Today, I'm going to finish up our module on random variate generation with a couple of more composition examples. Yesterday, we introduced this second method for generating random variates. Remember, the first one was the inverse transform method. The composition method is based on taking what can be a complicated distribution and breaking it up into its simple components. The tricky part being to figure out what the probabilities are for each of them. This is something which is actually called in the literature, what's called a mixture distribution, a mixture. That is, if you have a number of different random variables and you basically choose one with a certain probability, then it's called a mixture or a mixed distribution. And you can kind of think of it like this, that you have, let's say that you have a series of boxes, and each box is like a random variate generator. And so the way that this approach works is that you'll choose one of these, each time you do it, you choose a different box or potentially a different box. So let's say there were three of these boxes. Each box contains some random variate generator. So you can maybe imagine some little gnome inside who's creating values and then sticking them out. So each time you choose one of these with a certain probability and you see what value that is. And then the next time you basically throw the dice again to choose which box you're going to pick it out of, and then pick that one. So just to be clear, it's not that you say flip a coin or flip a three-sided coin in this case, pick a box and then always keep choosing from that box. No, each time you first choose a box at random, well, not totally at random, based on what the probabilities are. And then from the box that you've selected, you pick what the next generated value is. So in the algorithms, we will typically use one uniform, I've been calling it V, but you can call it whatever you want, and a second one to generate from the box that you've chosen. So the inverse transform method only requires one uniform random variate, but the composition approach always requires two, at least two. So if the boxes are using the inverse transform method, then you will just use one of these. Now, it's totally possible that the boxes themselves could be a mixture distribution as well. I mean, there's nothing to prevent that. There's probably not a good reason for that, because if one of these boxes were producing a mixture distribution, you could simply just sort of unpack that and just have more boxes. Okay, so just be clear about what this method is doing. So today I'm going to give just a couple more examples, and I hope you can kind of appreciate from the examples how what they do is they actually save you a bit of math. And in some cases, well, basically, if you can sort of slice and dice your distribution so that it looks simpler than what it is, then you can apply this method. This method has also been applied to approximate distributions that are challenging to generate from. Okay, what makes a distribution challenging? Well, if the CDF cannot be inverted, remember the whole basis of inverse transform was that we had this inverse CDF. And in all the examples that we've seen so far, we've been able to invert that. But there are random variables where you can't invert that. In other words, the functional form of the cumulative distribution function is such that there's no mathematical expression for the inverse. There's always a theoretical inverse. That is, this always exists. But for some distributions, you can't actually write it down. If you can't write it down, then you can't really apply the inverse transform method. Examples include the gamma distribution. The normal distribution, unfortunately, cannot be inverted that way. And so different things can be, different methods are typically needed for that. There are some special purpose method, that is, special methods that exploit the properties of the probability distributions. Again, we're not going to get into that. You can use the inverse, not the inverse transform method, but something called the acceptance rejection method. And again, for the interested student, a description of that is in the reading. And for you, that we're not going to be responsible for that because we need to get on to the final topic, which will start next Tuesday, which has to do with analyzing the output, which is in a way the punchline of the whole thing. And we could easily spend a whole quarter on that. In fact, there's a course in the operations research department that does exactly that. That is, given that you have a set of simulations that you've already developed, then they go into some very sophisticated ways of exploiting those, analyzing them to see what those simulations are telling us. We are going to basically dip our toes into that starting next week. But to finish up this week, I want to show you two examples of applying the composition method. And the first is something called the Laplace distribution. I'm not sure why they call it the Laplace distribution. Laplace, of course, was a famous mathematician. My conjecture is that it was kind of a consolation prize because Laplace actually was was using the Gaussian distribution before Gauss, and yet Gauss got his name on it. So maybe this is a consolation prize. But this is actually a very useful distribution in many contexts. Mathematically, it's a little more tractable than normal. This is its PDF. Its PDF looks like a symmetric function with in this case, a mode at 0. In other words, a spike at 0. So most of the probability for this is going to be located here. In contrast with the normal distribution, which is the old bell-shaped curve. Looks kind of like that. So you see the difference, but functionally, it looks like it sort of has the same kind of general shape, except it's pointier. What it is it's actually a bivariate exponential. That is, each side is like an exponential distribution. So this is this PDF, and so this is a graph of what that is. And then you can actually unravel the CDF so that on one side it looks like this for negative values of x. Again, so notice that these values are negative. So this exponential is actually going to be decreasing as x gets larger. in absolute value, it gets smaller in its negative. So this actually goes down, and it's symmetric this way. So you can certainly use the inverse transform method for this, because this is definitely invertible, but it would require you to kind of to fuss a bit. So instead, to save ourselves the math, what we do is we notice that we've already done exponential. Remember, exponential, I think what we were using gammas, I'm sorry, lambdas. If you remember, it was minus lambda times the log of 1 minus u. And that would give you this side right here. And then if we make that a plus, that is, we just take the minus of that, that would basically give us this side. So in other words, if we cut this in half and say, this is a mixture of one of these exponentials and one of these exponentials, and because it's symmetric, the probabilities are a half and a half, then we don't have to go through all the math of trying to unravel the CDF. Instead, we can just use composition. So with probability of a half, we generate, okay, and this should have been an uppercase, we generate a one on the positive side. So this would be this side, and then the other one would be on this side. So mathematically, would you rather do this or try to invert all this? Again, if you're so inclined, it would be an interesting exercise to do that. But the principle of laziness indicates that doing the composition method, exploiting the fact that we've already done the exponential, is the lazy way to go, and it's a reasonable way to go. So let's see how that plays out. If you do a pull on our source code here, you will find that there is a Laplace variate that, okay, so we have our parameter. And then notice that this is exactly, well, again, this is roughly what was done. What I did here was I just took a little bit of a shortcut. I said, okay, let's start with our regular exponential. But then if my v is less than a half, then I'll flip it. Okay, so this logically is the same as what's going on here. And, you know, with the parameters, we do this whole dance. We only need one parameter. It has to be a number. All of this is fairly straightforward. But the parameter has to be strictly bigger than 0. Otherwise, usually, as you can see, if our beta is equal to 0, we're just going to get nothing but zeros, and that's not okay. So again, with parameters, we should throw an exception if it's not a legal value. So to test it, again, just following the same structure as we had before, we tell our random variate factory to look in here. So here's, we get our instance here, and then we're just going to generate a whole boatload of them and save it this. So let's generate that, and we're done there. And again, so let's fire up jump and see whether or not that actually worked. So let's see, we want to import, and This is what was just generated. And that looks good. So we will import that. So we have our values now. We analyze the distribution. And we see that it kind of looks right. I'm not sure how, I'm I'm a relative newcomer to JUMP, so I'm not sure how to histogram options. Let's see. Standard error, set bin width, count axis. What I want is I want more. Let's see, can I set the minimum and the maximum? Count axis, probability axis.
Are you trying to get it to zoom in on the, or restrict the range of values?
Yeah. Do you know how to do that?
I believe I vaguely remember. You should be able to actually drag the numbers at the bottom. If you hover over it, a little hand should come up and allow you to drag left and right, and you can kind of scoop it in.
Like this? Oops.
Yes, sir.
Ah, okay. Thank you. Okay, yeah, that's pretty nice. Oops, wrong way. Yeah. Well, anyway, you yeah, I'm a little more, oh, okay. So that's what that is. Thank you. All right. So now the next one is kind of interesting. Again, this is, you're not going to see this distribution in your stats class, but this is actually a fairly useful distribution. The triangle distribution and distributions like this trapezoid are actually extremely useful, especially in situations where there's not a whole lot of data, but there might be a lot of information. In other words, it may be that the only information you have is on, let's say we're trying to fit a distribution to a simulation of a particular task. And you just don't have the data, and you don't have time to collect the data. But what you have is you have sort of some guy who's been working at the place for like a million years and kind of knows how things work. And so what you do is you basically gonna take him out for a beer and talk to him about, well, what's the fastest that this was ever done? And then what's the slowest that it was ever done? And that would kind of give you these kind of ranges here. And then you might say something like, well, most of the time, what is it between? I mean, okay, those are the extremes, but most of the time, about how long does it take, and so it might be, they might say, well, it's never taken less than this amount, and it's never taken more than this amount. And most of the time, it's kind of between these two guys. Okay, so basically you've given these four values. And so just to make a very simple distribution, I mean, if you look at it, it looks kind of like almost like a normal type of thing. And yet with a normal, you'd need sort of means and variances and stuff like that. But instead of that, you just have these four values. And a lot of times that can give you a good enough approximation to how this thing works. So this distribution, the PDF, this is a PDF that has the trapezoid shape. And the basis of it is just basically these four values. So finding the PDF and CDF, it's messy. It's absolutely doable. It's really not a problem at all. But it's kind of messy, prone to errors. But what we have, if we look at it, is we have three pieces that we've already done. We've already done a uniform with any range. We've done a triangle that looks like this, and we've done a triangle that looks like that. And so if we can decompose these into those two triangles and the rectangle, then we can apply the composition method without having to do a lot of math. Now, the only math that we do have to do, though, is to figure out what these probabilities are. So in other words, those probabilities are going to be the area under the curve. Because remember, the area under of a PDF is always 1, and the sum of the probabilities has to be 1. And so it turns out that the area under the curve of the PDF for each of the pieces are going to give the relative probabilities. So, but the one thing we don't know is what the height is. So that's the one bit of math that we do have to do. And so to do that, we need to find what this height is. But that's fairly straightforward, because all we got to do is add up. So if the height is h, and we don't know what that is yet, the P0 is going to be 1/2 the base times the height. So that's 1/2 of c minus a times the height. So that's the first one. The middle one, again, the area of a rectangle is the base times the height. So that's d minus c times the height. And then finally, the triangle over here is 1/2 the base times the height. So 1/2 the base times what this height is. So notice that h multiplies everything. And when you unravel all that, again, it's just very, very simple math, much simpler than trying to figure out the equation of these lines. And so we can find our probabilities, as in this case, you just multiply h times this probability here. So the 2's cancel, and we get c minus a over what's down here. And these are the three probabilities. And so to generate from this, again, we generate our u and our v. And then so here's how you deal with three different regions. And you just have to be a little careful, because what we have to do is accumulate the probability. So in other words, the first test is if v is less than our P0, then we're going to return our the triangle on the left. Otherwise, if it's less than the sum of these two probabilities, we're going to return the middle one. And then finally, if it's above that, then we're going to return the triangle on the right. So this one would be our triangle on the left. This would be the rectangle. And then this would be the triangle over here. Okay, so let's see what that looks like here. So I think, so we have a trapezoid variate again. So now we have 4 parameters. So we have left, I call them left, center right, and right. And then remember that there was that h thing that we had this, and since h kind of appears in all the probabilities, just for convenience, it's helpful to just sort of add an extra derived parameter. So that's, I call it height. So when we're setting our parameters, again, we need to worry, do we have all 4 parameters? If not, we're going to throw an exception. Are all the parameters numbers? If not, we're going to throw an exception. And if they're numbers, then we can safely cast them to numbers. And then here's where we set the height. So then here's our method. So again, we generate U and V. And then just a little principle that is sometimes I violate it, but I probably shouldn't, is that in any method, it's really best to only have one return statement at the very end of the method. That's sort of good. And especially if a method is a little bit more involved, as this is, it's we could have returned inside each here, but that's somewhat questionable style. Okay, so here's the first probability. Now I could have simplified this, but instead I just kind of wrote it out. Here's the first probability plus the second probability. And here we're returning simply the uniform. And then finally, here's the right triangle there. So again, we just kind of, here's the, I just kind of chose some values there. And let's see what that generated. Okay, so let's import our trapezoid. Okay, so now it's trying to do a fixed width field. I don't want that here. I want delimited, because see, it's trying to make columns out of those other things. So I don't want that. I just want, come on. There we go. And okay, so let's import that. And we see that what we have looks like a trapezoid. And what were the parameters? 1, 3, 5, and 7. So that'd be 1, roughly 3, roughly 5, and 7. If we look at the maximum is just a little bit less than 7. The minimum is just a little bit more than 1. And we see, just looking at the shape, it kind of flattens out here between 3 and 5, and then slopes down to 7. Okay, so that shows that we are in fact generating something which is according to the shape of our distribution. Okay. So now all of this would just be kind of an interesting exercise if we couldn't use this in a model. See, the purpose of having these different random variates is that in our simulation model, when there's a particular element of it that requires some kind of randomness, such as inter-arrival times, service times, renege times, all the different times that we've been using and have been modeled as some kind of random process. The whole idea of this is that if we are in a situation where we want to use one of these distributions, and the package we're using doesn't happen to have the distribution we want, then you should be able to define that distribution, implement that distribution, and then use that as a first-class citizen. And that's what SimKit does. So we've seen that if I've defined a user random variate, then I can tell the random variate factory, which is the factory that produces all these, to add the package that it's in as a search package. And that lets the random variate factory kind of look for random variates in the given package. Now, you need to be sure that the code is compiled. So if it's not compiled, it's not going to find it. So in NetBeans, then what you want to do is kind of turn on compile as save, or just make sure that you recompile it as it's edited. So we can use our random variate factory to get the random variate instance, passing the desired parameters, and then we can apply that instance in any sim entity that has a random variate. Okay, so let's see an example of this. I don't have one that I've committed, but let's see. Let's take our entity server. So let's, I'm just gonna, okay, run an entity server. I'll just call it run entity server 1, that's fine. Okay, and if you remember, we had a uniform inter-arrival times between 0.9 and 2.2, and we had gamma service times. And this worked because SimKit has the uniform distribution and it has the gamma distribution. It actually has a fairly robust list of a lot of the standard random variates, but it doesn't have a complete list. And in fact, no package that you'll find will have every single random variant that's out there. So in particular, this Laplace distribution that we just did and this trapezoid distribution that we just did, those are not in SimKit. So what if I wanted to use, well, I don't want to do the Laplace distribution. Let's use the, let's see, we had did we have a triangle distribution? I believe we did. Okay, we had a yeah, we had a triangle here. Okay, so let's make this a triangle, and instead of uniform 0.9 to 2.2, and then let's put the mode at say 1.1. And then now it's not going to find the one I want unless I add the search package to mv3302.random. Again, it's not, the search package I'm adding is not the package I'm in. See, I'm in mv3302.run, but the random variables I want are in mv3302.random. So that in particular, the triangle that I want is in there. And let's use the trapezoid for our for the other one. And now, okay, this is a sorry. So let's maybe go from 1 to 4 on the outside, and let's 2 and 3 on the. I'm not sure how that's going to behave, but let's kind of see. So so what I've done now, remember when this, and notice that I have not edited the entity server itself. I'm only editing the main class. That's all I need. And it will use the triangle and the trapezoid, neither of which existed when the entity server was written, or the arrival process for that matter. So hopefully this will kind of work. Okay, so remember we always did a print line of our processes. And so this showed that the inter-arrival time was in fact our triangle distribution using composition, and that our service time generator was using our trapezoid with the right parameters. Let's verify the parameters. 0.9, 1.1, and 2, check. 1, 2, and 1, 2, 3, 4, check. Okay, we had a bunch of arrivals, a bunch served. average number in Q, average delay in Q, and then the little formula thing, everything that we did before now used these new distributions. Okay, so so in other words, this whole business, this is kind of why do this. If we are in a situation where we say, well, our inter-arrival time generator needs to be a triangle distribution, and our service time happens to have this trapezoid thing. Okay, where did that come from? We figured that out somehow. If you're in a situation where your model requires a given distribution and your package does not provide it, then what you now have is the ability to implement that distribution. I mean, you need to do a bit of work first to figure out a way to do it. That is, find the algorithm. And then here for our triangle and our trapezoid, these were both ones that we implemented using the composition method. But what method they use is less important, is the fact that it uses some method. So a distribution that didn't exist can now be used as a first-class citizen. In other words, the random variate factory, now that it's kind of looking in the right place, just goes, it defines this. Now, why does the random variate we have to go through the random variate factory? Because it's the random variate factory that sets the underlying random number generator, which in this case is a Mersenne twister, but could be any of the others. You can configure it. And so every one of these random variates that I get from the random variate factory uses the same underlying random number generator. Why is that important? That is important because that guarantees that these are going to be independent. In other words, say the first inter-arrival time that it generates, it will use, in this case, the first two random numbers from the underlying random number generator. And then the first service time will use the next two for its trapezoid. And then which ones they use is going to depend on how they get mixed up. If the next, so let's say the next two are arrivals. So I get two more arrivals, and so it'll pull the next four random numbers from the underlying random number object. And that will guarantee that these two are going to be independent one from the other. And that's how the random variate factory works.